So what we're going to be doing today is volumes by cross-section. Or volumes created by cross-sections. So I think I'll try to draw the picture first, and then we'll look at some pictures, because these are 3D things, so it's really tricky to, even if I was a perfect drawer, which I'm not, it would be tricky to see what's going on. So we're going to do one example like 3 different ways. So let's have a base of x squared plus y squared equals 16. So what shape is that?
Circle.
A circle, good. So I'm going to do a circle, radius 4, that's not a bad circle there. That's going to be my base. Coming up out of the circle, I'm going to build some cross sections, and we're going to do a variety of different ones. Probably the easiest one to compute, and maybe even visualize, is let's have square cross sections on our circle base. The squares are going to be coming up out of the page on from the circle that we have there. Looking for a little one here. Yeah, that'll work. So here's a square that is about, well, I'll make it work. The square is going to be the one that right at the middle. There we go. So the middle square coming up out of the page looks like that. It's hard to see that on camera. So it's coming straight up out of the page. Tilt my camera there a little bit. You can kind of see what's going on. And so there's a square there, and then there's a square next to it, and next to it, and next to it, but they get smaller and smaller. See if we can make some smaller squares here. So maybe there's a square right there. It's sort of set in the circle, but it comes up out of the page. And if I made an even smaller one, tweezers to hold this one. That one would be way over on that side, just barely right there. So it's not as high, as tall as the other ones. I'm trying to help our online friends see what's going on here. So you got that one there, and you got this one here, and you got that middle one in there. And in fact, it's all filled in, so it creates a solid. But each cross section is a square. Yes, no? So, okay.
So are the squares, like, are they lines or do they have volume?
So each square, it's a good question. Are the squares lines or do they have volume? Their thickness, so you're actually going to add up all the areas. So you can think of the square as having an area, and its thickness is super thin. Our square cross sections with thickness of dx. Right? So it's super small, just this really small dx. Its thickness is just really small. Its width, though, is, or its side length, I guess I should say. I guess I could make one of these match. So there's its side length. And so each of these volume squares is S by S by dx, its thickness. Which is almost to the formula. Let me show you some pictures that might help. This is frequently one of the projects that people do, that calculus teachers do. So you Google volumes by cross-section and you get, there's not one that matches exactly what we did. So this picture here, so we get a bigger version of it. That was a bigger picture than, there we go. So the base is x squared. You can kind of see that. The black line is a parabola. And this one up here has cross sections of squares. This one right here has cross sections of semicircles. That looks like cross sections of some kind of rectangle. And that is maybe some kind of triangle. So they can get complicated. Right now we're going to work on some whoops. There we go. We're looking at one with cross sections of squares. So does this help visualize what we're looking at? Again, if you want to see pictures, you just Google volumes by cross-section, and you can see, you know, projects that kids have done. There's computer animations. Here's pretty close to what we're doing. So their circle, rather than drawing just the top view, they've kind of slanted the circle to make it 3D. So there's the y-axis and the x-axis. Their circle is radius 1, but then they're showing you the cross sections of squares coming up out of the page. They're just kind of tricky to draw. So this person did the flat xy and then tried to 3D the squares coming out of the page. See if there's any other good pictures. Let's see, there's one with semicircles, another one with semicircles. There's one with squares. This is a good one because, let's see if we get a good picture of it. This one is sort of modeling it with different thicknesses of squares. Now, our thicknesses are going to get infinitely thin. Like this would not be a very good volume, right? That wouldn't be a very good approximation with only 4 squares in there. This one would be a really good approximation of the volume. So our dx, or our thickness, is going to go to dx. Let's see if there's any others we should look at. Some of them are hard to see what's going on. I think we're out of the helpful pictures here. Yeah, I don't think there's anything else that's helpful. There's another one with a circle base and squares coming up out of the page right there. There's some more homemade projects with some base, and got some semicircles and some squares and semicircles, some triangles. Those look like equilateral triangles even. So, and those are equilateral triangles. All right, so let's go back to our problem now. So we've got these squares coming up out of the page, and we want to add up all of the volumes. We want to let's see, let's add all the volumes. So add means sum, but the Greek letter S for sum, that's like a finite sum. We want an infinite sum. Remember this, that integral symbol looks kind of like an S because it means sum. It's not an accident. That means sum up all of the volumes. Well, the volume would be, let's see, here's our little square. S times S, and its thickness we said was dx. So I need to figure out what S is, though. There's S. That height is Y. So, let's see. It looks like S is equal to 2Y. So this would be the integral. Oh, I can put limits on here because I know I'm adding up the rectangles from -4 to 4. Or adding up the squares from -4 to 4. S squared is 2Y squared. I can't integrate yet because I've got Y's and X's, so that's a bit of a problem. So let's square the 2, take the 4 out. Y squared. But we know what Y squared is equal to. Y squared is equal to 16 minus X squared. Oops, that's off the 4. Well, now this is calculator ready, so this is a calculator problem once you get it set up. But the setup is hard enough, so Math 9, -4 to 4. $85.333. But I'm not really worried about the calculator part. I'm worried about getting it set up and being able to visualize what's going on. Oh, wait a minute. You know what I did? This is a very common mistake. That's not the right answer. I forgot to do something even worse than that. I forgot to multiply by 4. So I put the integral in right, I just forgot to multiply by 4. It's kind of a common mistake, and I probably should have avoided it if I'd just started with the 4. But whatever, times 4, 341.333. Good catch. Yes, you can math frac that if you want. Again, it's hard to visualize, it's hard to draw it, and I'm worried if I draw more, it makes it worse. So like here's the square coming out of the page. And over here, maybe there's a really small square coming out of the page. But if you try to draw too many, then it turns into a mess. Let's do another one. Same base, but with semicircles. So there's my sort of top view looking down on XY plane. There's a semicircle coming up out of the page. It looks like just a bump on the side of a circle there. Semicircles coming up out of the page. I don't have any circles cut out to show. Can you visualize what that looks like, or do we want to look for another picture? There was a picture with semicircles somewhere in here. This one had semicircles, yeah. So the base wasn't a circle, the base was this parabola looking thing, but it has all these semicircles coming up out of the page. So that's what we're gonna do next. Let's see if there's any other semicircles. circle. All those have a base circle. All right, so we want to add up all the areas. Well, sometimes I say area, sometimes I say volumes. If you call it a volume if you include the dx. If you just want to stick the dx on the end and add up the areas, that's fine too, as long as there's a dx at the end. So again, we'll go -4 to 4. Although with the symmetry in there, you could go 0 to 4 and multiply by 2, if that's easier. Although in the calculator, it doesn't really matter. So I want to add up all the areas of the semicircle. And we're slicing dx. We're slicing along the x-axis. All right, well, a semicircle, let's come out to the side here. The area of a semicircle is 1/2 pi r squared. That's my r. This one in some ways is easier than the squares because that r is also equal to my y. That's that point right there of x comma y. R is the y height. So area is 1/2 pi times y squared. That's better, but I need everything in terms of x so that I can put it in the calculator and integrate. But y squared, let's see, this was x squared plus y squared equals 16. So y squared was 16 minus x squared. So from -4 to 4, the area of the semicircle is 1/2 pi 16 minus x squared dx. Now that's just a calculator problem if we make it that far. Math 9. -4 to 4. I could slide the constants out. I can leave them in, doesn't matter. Pi over 2 times 16 minus x squared dx and 34.041. You know what? I'm going to switch courses here and make my next problem match one of these pictures. I want to do a triangle with a different base. So where did that... Here we go. So let's do that yellow problem back there. So I'm going to say that's it. I don't know, you can't quite tell. Let's call those equilateral triangles. And let's say the base is y equals x squared. Base, these are worded kind of weird, but it's formed by y equals x squared, y equals 0, from x equals 0 to x equals 1. We'll just keep it simple, or as simple as we can make it anyway. So from 0 to 1, we got a parabola drawn in there. That's my base. I don't want the area of that base. That would just be the integral from 0 to 1 of x squared. That's not what I want. Now I want to form a solid with equilateral triangle with equilateral triangles as cross sections, I guess I should say. So on the far end, I've got this big triangle coming up out of the page. You know, halfway through it's a little bit smaller. Over here it's even smaller, smaller, and so on. So I want to add up all of the triangles. So add up. I'm slicing dx, so I know it's going to be dx. That means my limits need to be in x. So what are my limits going to be? From what to what? 0 to 1. I'm adding up all the triangles from 0 to 1. And I don't want to jump straight to a formula because I don't know what formula is going in there. So I kind of do this halfway thing where I say the area of equilateral triangles. And then I need to go figure out what the area of an equilateral triangle is. Or maybe I remember it from warm-ups. Or if I don't remember it, I at least remember that I wrote it down somewhere. Square root of 3 over 4 times s squared. Where this is s. This is s. So what's s equal to in terms of x or y? It's the y. It's the height of the curve right there. If that point is xy, then s is equal to y. So this is root 3 over 4 times y squared. Okay, that's getting better. I went from a sort of generic formula to a formula that's closer to what I'm using. But if I'm slicing with dx, I don't want to put a y in there. So what's y equal to? X squared. So s equals y. But y equals x squared. So root 3 over 4 times x squared squared. So from 0 to 1, root 3 over 4, which could go outside the integral, x to the 4th dx. And that one wouldn't be awful to do by hand, because it would just be x to the 5th over 5, and you'd have 1s and 0s to plug in. But we like our calculator, so why not? 0 to 1. I'm gonna go all out here and make it look just like I wrote it. Root 3 over 4 times the integral from 0 to 1, x to the 4th dx. 0.086 or 0.087, I guess, if we're rounding. That seems small, but think about the dimensions here. It's only 1 wide and 1 high, and it's not even all of that, so it should be way less than 1. So that kind of makes sense. All right, let me so looking at the homework, well, if I cross-section homework, 7b was already omitted. You can throw out the isosceles right triangle problems, primarily because this particular worksheet doesn't say if what the orientation of the right triangle is. Is the base on the graph or is the hypotenuse on the graph? And it matters, and it doesn't say, so we gotta throw those out. So part C, throw those out. Number 10, you can throw that out, and so that doesn't leave a whole lot left. Let's do 7A is kind of a review problem, so we'll come back to that later, because it's not a volume problem, it's an area problem. But let's try together one from number 9. That looks weird. We've done one of each of those. You got a preference on whether we do the square, the equilateral triangle, or the semicircle? The triangle, because it's worse. Okay. So maybe before I even start, area of an equilateral triangle, while it's still sort of fresh in my brain, is root 3 over 4 times s squared. So jot that down, and then we'll focus on the rest of this problem. All right, find the volume of a solid whose base is bounded by these curves with the indicated cross sections, and we're going to do the equilateral triangles. All right, we omitted C, so maybe we could do our graph sort of in this area down here. All right, well, I need to know what these two graphs look like. Y equals x, that's an easy one. The other one, I'm going to do a table of values for. You could do it in the calculator, but you just have to be super careful. Although I guess you could do a calculator with table of values and kind of combine the two methods. If x is 0, y is negative 3. X is 1. See, 1 minus 1 minus 3 is also negative 3. That immediately makes me think I'm doing something wrong, but I think I'm right. We do 2. 4 minus 2 is 2. 2 minus 3 is negative 1. We do x equals 3. 9 minus 3 minus 3, 9 minus 6 is 3. That's going to land on y equals x. So there's our intersection right there. Let's go back the other way. Let's look at negative 1. So that'd be 1 plus 1 is 2 minus 3 is negative 1. Oh, there's our other intersection. So yesterday we found the area of that thing. That'd be the integral from negative 1 to 3 of top minus bottom. But that's not what we're doing today. Now we're building triangles. And you don't want to draw too many in. I think it's crazy, but I have triangles coming up out of the page off of that base. So I think it's helpful to draw one. I think it gets confusing if you draw more than one. I guess if you could draw one on each end, maybe that would be helpful. But if you draw any more than two, things get kind of crazy looking. All right, so I want to add up all of the triangles that are there. So the volume is the sum, the integral, the antiderivative, from what to what? Negative 1 to 3, because those were the intersections. So that makes the sort of bounds where we're looking at. And we're adding up the area of a triangle, which I already wrote. So I'm going to put root 3 over 4 times s squared in there. But I need to now figure out what is S equal to. This is sort of related to what we did yesterday. What's S equal to? Or how do I find S? It's the top minus the bottom. So that's y2 minus y1. So y2 is the line, just x, minus y1 is the parabola, x squared minus x minus 3. And although it wouldn't be my favorite if you left it like that and went to the calculator and gave me an answer, it would be acceptable because this is what's going in the calculator and you told me what S is. So if you're really trying to save time, you could put this in the calculator as long as you put this in for S. I'm going to back up a little bit. Not back up, I'm going to show what would go in the calculator. So the root 3 over 4 out front. And then x minus x squared minus x minus 3 squared dx. That adds up all of the equilateral triangles from -1 to 3. Math 9. I'm going to put the root 3 over 4 out front so I don't forget it. But if that annoys you, you can put it in later, although, again, you already saw me forget it once today, so that's why I'm putting it in at the beginning. -1 to 3, x minus. Now you can distribute the negative sign on your own and put it in, or you can let the calculator do it with parentheses. I don't know whichever one's easier for you to keep track of. 4.619 would be the volume of all of those triangles coming up out of that weirdly shaped base.
How do you put the square in there?
Uh-oh, I don't know that I put the squared in there, now that I mention it, or now that you mention it. Yeah, I didn't square it. So I probably need an extra parentheses to account for the square. Oops. There we go. So I put an extra parentheses in there so I can get it all, make sure I'm squaring the right thing. Yeah. $14.780. We've talked about this before, but if you had put the things in the calculator to look at them, x squared minus x minus 3 and y equals x, then it might be easy to -1 to 3. So now I'm just doing y1 minus y2, I think. Nope, y2 minus y1 squared. So extra parentheses, bars y2 minus bars y1, close parentheses squared, dx. That should give me the same answer. Oh, put it where you can see it. Yeah, it did. So if you like using the y-var thing, you can. Especially if you've already typed it in the calculator to see what the base looks like. And we usually group these problems because when you do semicircles, actually let's do squares. The area of a square is side squared, but we already know what side is, what S is equal to. That's true for all of these. So it's kind of helpful that they put these in groups usually, because once you have S, it's the same S for all of them. You're just kind of doing different stuff with it. All right, so we're adding up squares, adding up triangles, adding up semicircles. Friday we'll add up circles, but that's Friday. So homework is to finish this. I'll do some more and post some answers later. But please keep up with this stuff so it doesn't pass you by.